Hi, let's take a look at an example using Kepler's third law of motion, and one of the problems that I've talked about in another video. Say we want to take a look at the International Space Station. Well, if it's orbiting Earth with a radial distance of 6.6 times 10 to the 6th meters from the center of Earth, using a value of 9.8 meters per second squared for the strength of gravity isn't necessarily going to give us a precise answer. But Kepler's third law will. And Kepler's third law tells us the period squared is 4 pi squared divided by the universal gravity constant, the mass of the object at the center of our orbit, so the mass of Earth, times the radius of the object's orbit cubed. So if I take the square root of that, the period's going to be 2 pi divided by the square root of the gravity constant times the mass of Earth times the radius of the International Space Station's orbit to the 3/2 power. So cubed and then square root. So that period, 2 pi, 6.6 times 10 to the 6 meters to the 3/2 power, divided by the square root of 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared, times 5.98 times 10 to the 24 kilograms, gives me a value of 5,330 seconds, which is just about 90 minutes. I think it's 89.5 minutes, which is the minimum period that you would find for the International Space Station, which is the period that it has in its lowest orbit. As you go up to higher orbits, the orbital period time increases, and if you were to head all the way out to the moon's distance at 7.35 times 10 to the 8 meters away from the center of Earth, you get a time of 27.4 days using Kepler's third law. Thanks for watching.